Ever feel like really important ideas are just locked away behind confusing words?
Yeah, like you need some kind of special key just to get what's going on.
Exactly. That's what we try to do here at the Deep Dive. We take those complex topics, those tricky concepts.
And we boil them down, get to the core insights, the stuff that actually clicks.
Think of us as your shortcut to really understanding things thoroughly.
And today, we're diving into design algorithms and optimization.
Right. We've got some material from a data in design course that a listener shared. Looks like a lecture video and a summary report.
Our mission, to unpack these concepts, see what they really mean for design, and, maybe surprisingly, how relevant they are for anyone wanting to grasp complex stuff quickly.
Okay, design algorithms, optimization. Still sounds pretty technical, maybe a bit dry.
Well, it can sound that way.
But the lecture we looked at, it didn't really frame it like that. It felt much bigger, more fundamental.
Yeah, the initial framing was surprisingly broad. It wasn't just about code or math equations.
It suggested these ideas are, like, woven right into the act of designing itself.
Absolutely. And that's one of the core challenges to the traditional view, isn't it? That these aren't just separate technical fields.
Mm-hmm.
The lecture argues they're actually part of designing.
Yeah.
You hear terms like parametric, agent-based, data-driven,
I
procedural.
suppose buzzwords.
Yeah, but the point was, these aren't just software types. They represent the intention behind the design. They how and why you're approaching the creation process.
Okay, so shifting from the tool to the thinking, that makes sense.
And that leads to this really powerful central idea the lecture put forward,
Which is?
that design, engineering, algorithm, and optimizer are, in fact, all the same thing.
Whoa, okay. That's a bold statement. How does that work?
Well, think about it. Any design process involves steps,
All right.
a sequence.
Sure.
That's basically an algorithm.
Okay.
And you're usually aiming for some desired outcome, trying to make it better according to certain criteria.
Which is the optimization part.
Exactly. Even sketching, you're making decisions, refining. It's a process with steps towards a goal. An algorithm, really.
So whether you're focused on aesthetics or, say, safety, like an engineer.
You're still following steps to achieve goals.
Mhm.
But the mindsets can differ, and that's important here.
Right. The lecture talked about that contrast. Designers may be thinking concept aesthetics.
Mm-hmm. And engineers focusing on safety, reliability, making sure it works predictably.
But both are using a structured process.
Yes. And here's the crucial bit for designers wanting to use computational tools effectively.
Uh-huh.
The lecture stressed understanding the engineering mindset, specifically like software engineers,
Meaning not becoming coders, but
but appreciating things like numerical thinking, breaking problems down logically, setting up systematic pipelines or workflows.
okay. So understanding that structure helps translate design ideas into something a computer can work with.
Precisely. Without that, the lecture suggests using these powerful tools effectively is, well, it's a struggle.
And this all comes back to one key thing the lecturer really hammered home.
Computational thinking.
Yeah.
They even switched to Korean briefly to emphasize it. Vijin Lijin, Gilandin, think that ball. It's that fundamental.
So what is computational thinking really? It's not just thinking like a computer, is it?
No, not exactly. It's more a problem-solving approach. Breaking things down, decomposition, focusing on what matters, abstraction.
Seeing patterns.
Right, pattern recognition, and then developing step-by-step solutions. That's the algorithmic formulation.
It's about making your implicit design knowledge, your intuition, more explicit, more structured.
Exactly. And the interesting point was that designers, because they already understand design so deeply.
They're actually in a great position to apply this computational thinking within design.
Yeah, that existing knowledge is a huge advantage.
Yeah.
Okay, so from that foundation, the lecture then kind of builds up our understanding by looking at different types of algorithms.
Right, the building blocks. First up was deterministic versus stochastic.
Yeah. Deterministic is predictable. Like 3 plus 3 always equals 6. Same input, same output. Every time.
Crucial for things where you can't have surprises, like safety systems.
Definitely. Stochastic, on the other hand, involves randomness or probability. Think weather forecasts, slightly different starting points might lead to different outcomes.
So in design, stochastic could be for exploring possibilities, generating variations.
Exactly. Introduce some controlled randomness to see what emerges.
Okay. Then brute force versus heuristic sounds like effort versus cleverness.
Huh. Yeah, that's a good way to think about it. Brute force is trying everything, like every single combination on a lock.
Guaranteed to work.
Yeah.
Eventually. Probably very slowly.
Right. Very resource intensive. Heuristics are more like shortcuts, rules of thumb. Think of a sat nav finding a pretty good route quickly. based on usual traffic.
Efficient usually gets you there, but maybe not the absolute perfect shortest path every single time.
Precisely. It's a trade-off. Thoroughness versus speed.
Got it. Next, DFS and BFS. Sounds like search patterns.
They are. Depth-first search, DFS, is like exploring a maze path all the way to the end, then backtracking if it's a dead end.
Going deep first.
Yep. Breadth-first search, BFS, is more level by level. Check all the rooms connected to the start, then all rooms connected to those, and so on.
Going wider. Why
Yeah.
choose one over the other?
Well, BFS is often good for finding the shortest path, like we mentioned. If you need to ensure you've checked everything closest first, BFS is your go-to. Think evacuation routes.
Okay, makes sense. DFS for deep dives, BFS for finding the nearest or shortest. Now, greedy algorithm sounds a bit selfish.
Uh-huh. Well, the lecturer put it simply.
웃겨. You just do what seems best right now.
Like making change. You always give the biggest coin possible first.
That's the classic example. In design, maybe you'd sort building options by like a wow factor score and just pick the highest ones first.
Or minimize lights needed for artwork coverage by picking the light that covers the most new art each time. Exactly. But the lecturer also pointed out the downside. That immediate gain might not lead to the best overall solution. The change example works, but prioritizing popular amenities centrally might ignore people further out.
Right, short-term gain versus the bigger picture. Okay, then simulation and state change. Modeling things over time.
Yep. Like traffic lights changing red, yellow, green. That's a state change. Or a bus queue, people arrive, bus comes, people leave. The state, number of people waiting, changes. You model the rules and see how it evolves.
And finally, recursion and divide and conquer. These sound a bit more complex.
They can be powerful. Recursion is basically a function calling itself to solve smaller bits of the same problem, like Russian dolls.
Okay.
Divide and conquer is breaking a big problem into smaller separate ones, solving those, then combining the answers. Sorting a huge list by splitting it, sorting the halves, then merging them is a common example.
Right. Break it down, solve the pieces, put it back together.
Okay.
So those are the algorithm types. But they need data to work on, right? Which needs organizing. Data structures.
Exactly. You need ways to store and manage the data efficiently. The lecture covered key ones, linear ones first, like arrays and lists data in sequence.
One after another.
Yeah. Linked lists were mentioned where each item points to the next, making it easier to insert or delete things compared to a fixed array.
And nonlinear, for more complex connections.
Right. Like graphs. Super important. The lecture really emphasized these for spatial stuff.
Why graphs specifically?
Well, as the lecturer said, you go. They're basically perfectly suited for representing spatial information. Think connections between rooms, roads in a city.
Ah, representing relationships between places or things makes sense.
Then you have trees, hierarchical, like a file system folder structure or a family tree. Parent-child relationship.
Okay. And hash tables.
Those are for quick lookups. You use a key to find its associated value really fast.
Got it. Graphs for connections, trees for hierarchy, hash tables for speed. What about stacks and queues?
Those are about managing data flow. Stacks are last in, first out, LIFO. Like a stack of plates, last one on is the first one off.
And queues.
First in, first out, FIFO. Like a waiting line, first person in is the first person served. They manage the order of things.
Okay, so we've got the algorithms, the methods, and the data structures, the organization. How does this actually look when applied to, real design problems?
Yeah, let's make it concrete. The lecture had good examples. Solution space search. Think circle packing.
Yeah.
How many circles can you fit in a box?
Right.
Different algorithms, brute force, trying everything, greedy, placing the next circle wherever it fits best now, maybe even random placement. They give totally different results. Different packing densities.
So the algorithm choice directly impacts the design outcome. It's not just academic.
Not at all. We also saw the greedy example for sorting building designs by some metric, like aesthetics to height ratio. Or using a greedy approach to place the minimum number of lights to cover all the art in a gallery.
Fascinating how these abstract ideas solve tangible problems. And the graphs for spatial stuff seemed really powerful.
Hugely. Remember those mini examples? Moving overlapping boxes by treating context as a graph.
Yeah, and the sheep versus wolves thing in connected areas.
Pathfinding for big units that can't fit everywhere. Fire spread simulation and finding escape routes.
Even grouping things like the cabbage patches.
Exactly. It turns spatial relationships into something computable, analyzable.
And pathfinding itself uses these graph algorithms like DFS and BFS.
Yes, and more advanced ones like Q-learning were mentioned briefly. Finding the best path, maybe considering costs or avoiding obstacles like the monster avoidance example.
Right, and underpinning all this computational geometry is actual geometry.
Absolutely. Basic stuff like checking if a point is inside a shape, vector math, breaking shapes into triangles, triangulation. These are the fundamental building blocks.
Like those early vector exercises we did in the course material, it all
It
connects.
really does. They form that bottom-up foundation.
So understanding this stuff, algorithms, data structures, it's not just for computer scientists. It seems really relevant for designers today, maybe even relates to coding skills.
Definitely. The lecture touched on coding tests, how understanding algorithms helps with that kind of problem-solving assessment.
Even if designers aren't writing production code, the thinking is useful.
Right. And concepts like time and space complexity, how efficient an algorithm is, while maybe not a daily concern for designers in the same way as for software engineers, the principle of efficiency matters.
Sorting data came up too. Seems fundamental.
It is. And the lecture even listed typical coding problem categories: implementation, math, data structures, graph theory, geometry.
Hmm.
It shows how widely these concepts apply.
Like learning the grammar of computational design. It helps you use the tools, understand the logic.
Exactly. Understanding these fundamentals lets designers be clearer about their intentions, explore more options systematically, and ultimately optimize their designs based on actual criteria.
So what's the big takeaway for you, the listener?
Well, it's realizing design isn't just intuition. There's often a structured process involved, steps and choices.
Algorithms in action, even if you don't call them that.
Right, and developing that computational thinking, understanding algorithms, is becoming fundamental for designers working with data and digital tools.
It empowers you to formalize your process, explore more, optimize better.
Precisely. It unlocks new ways of working.
So here's a final thought. Think about your own design process. Where might you already be using algorithmic thinking without labeling it?
Yeah, those repetitive tasks, the sequences you follow to refine something.
How could being more conscious of that underlying algorithmic structure maybe open up new creative paths or make things more efficient?
Maybe even, just out of curiosity, check out some design-focused computational thinking resources or visual programming tools.
You might just spot the hidden algorithms in your own work and spark some completely new ideas.